Solving the Kepler problem using only Newton's laws, high school level math, and an intuitive approach to the concept of limits. Video 5, the final exam. This final exam will test our knowledge of orbital mechanics. Given the following initial conditions, find the equation for the orbit of planet Q. Planet Q is orbiting the Sun. And at a particular moment in time, its velocity, its distance from the Sun, and the angle phi are given in the diagram that follows. These quantities all have the subscript lowercase I to indicate that they are all among our initial conditions. R sub I equals 1.28 astronomical units, V sub I equals 7.321 astronomical units per year, and phi sub I equals 2.023 radians. Note that the orientation of the major axis of the orbital ellipse is unknown, so we don't know the planet's angular position relative to our reference direction. That is, we don't know the value of theta at this particular moment in time. We will eventually find theta sub I, and simultaneously we will find E, the eccentricity of the orbit. To find them simultaneously, we will need two equations containing these two unknowns. This is the general equation for an elliptical orbit that we have been using. We don't know r sub p, the distance of Q from the Sun at perihelion. More importantly, I don't know how to find r sub p without finding the equation for this orbit first. Instead of trying to find r sub p, we will find a different way of expressing the numerator, and then we will find the numerical value of the numerator. Note that, as before, r sub p could also be written r sub 0, because we choose our coordinate system such that when Q is at perihelion, its angular position is 0 degrees. Once we have a numerical value for the numerator, we can plug in r sub I for r sub theta on the left-hand side, and we will have one equation with our two unknowns. Before we do all that, however, we will find an equation for v sub I as a function of theta sub I and E. These will be our two equations with two unknowns. And they will allow us to find theta sub I and E. So let's get started. The first thing we can do is find dA dt, that is, the constant k for planet Q, from the information given. We can calculate it based on the three given initial conditions. Plugging in these numerical values, we get 4.217 astronomical units squared per year. We are going to need a new dV circle, and you recall that our equation for the dV circle is dV equals the quantity g times m divided by r sub p times v naught, all times d theta. As before, gm divided by r sub p times v naught equals capital R, the radius of our dV circle. In this case, we don't know Rp, as I have said, or V naught, but we do know their product because K equals 1/2 times R sub P times V naught, or 2K equals R sub P times V naught. We found K moments ago, and 2K equals 8.433 astronomical units squared per year. G times M, as it happens, equals 40 astronomical units cubed per year squared. When we do the calculation, we find that capital R equals 4.743 astronomical units per year. So we can draw our new DV circle centered at P1 with a radius capital R. We don't know the magnitude of V naught, but because Q has a velocity of V naught at perihelion, we know its orientation relative to our reference direction. We also know that the magnitude of V naught is the maximum speed of Q. For our purposes, we can put its tail at an arbitrary point, P2. Let's draw a dotted line from P2 to the bottom of the DV circle, thus forming, along with V naught, a diameter of the DV circle. As we learned previously, the distance from P1 to P2 equals E times capital R. We don't know the actual orientation, of course, of V sub I, but we can draw it in anyway, such that it connects P2 to an arbitrary point on the DV circle P3. We draw a radius from P1 to P3, and I can show you a presumptive theta sub I according to the rules of the DV circle. P4 is a point on the dotted line such that the line segment connecting P3 to P4 is perpendicular to the diameter that we have constructed. The length of segment P3, P4 is capital R times sine theta. The length of segment P2, P4 is capital R times cosine theta minus E times capital R. Now consider triangle P2, P3, P4. According to the Pythagorean theorem, we can write the following equation. Which I've circled here in pink. Expanding the second term on the right, we get this result. And when we factor out capital R squared on the right, we see that there will be a sum of sine squared theta sub I plus cosine squared theta sub I, which of course equals 1. So simplifying, we get the following. V sub I squared equals capital R squared times the quantity 1 minus 2e cosine theta sub I plus e squared. We can take the square root of both sides to get this formula for V sub I. We have thus achieved one of our main goals. We have found an expression for V sub I as a function of theta and E. We know what R is for planet Q's orbit. And we know V sub I from our initial conditions. So let's plug those values in. And we will save this equation for later. Now we need to express R sub I as a function of theta sub I and E. As I mentioned earlier, the first step will be to find another way of expressing the numerator on the right-hand side of this equation. The next several steps will not be obvious, and they will require a little bit more knowledge about the geometry of ellipses than we have required so far. First, we will show that the numerator given here equals a times the quantity 1 minus e squared. You will recall that e, the eccentricity of the ellipse, is defined as c divided by a, as shown in this diagram. So c equals a times e. Recall also that r sub p equals a minus c. Substituting for c and simplifying, we get r sub p equals a times the quantity 1 minus e. When we go back and substitute for r sub p in our general equation for an ellipse, we get this expression, which we can simplify so that we see that r sub theta equals a times the quantity 1 minus e squared, all divided by 1 plus e times cosine theta. Now it's time to explore the geometry of ellipses a little bit further. This diagram should look familiar to you, and of course we can replace c with a times e. Now we will draw a line segment from F2 perpendicular to the major axis up to a point P on the ellipse. This line segment is the semilatus rectum, and we designate it and its length with a small l. Our next goal is to show that the numerator of our formula for an ellipse equals L. Getting back to our diagram, if we draw a line from P to F1, we immediately realize that its length must be 2a minus L, based on one of the defining features of an ellipse. Now, from the Pythagorean theorem, we get this equation. Let's do a little algebra. We can expand both sides. And we can subtract L squared from both sides. And divide both sides by 4a. Suddenly, things look a lot less messy, and we can solve for L. After factoring out a on the right, we find that L equals a times the quantity 1 minus e squared. And we have just shown that L is in fact equal to the numerator in our equation for r sub theta. We are making excellent progress, but now we want to find the actual numerical value of L for planet Q's orbit. Let's go back to our diagram. Given our newfound expression for L, we can update the expression for the hypotenuse of the triangle that we have created. 2a minus L equals 2a minus a times the quantity 1 minus e squared. After some simple algebraic manipulations, we find that the hypotenuse equals a times the quantity 1 plus e squared. This is where things start to really get interesting. We want to imagine now planet Q at point P and focus in on that region. Remembering our standard reference direction, we see that the angular position of planet Q is 90 degrees. Let's draw in the velocity vector. Remember that it is tangent to the orbital path at point P. We label it v sub 90. Here I am showing you phi sub 90. And we note that now we can also think of L as r sub 90. So how will we obtain the numerical value for L? We begin by expressing K in terms of these three quantities for planet Q when it is at an angular position of 90 degrees. That is, K equals 1/2 times r sub 90 times v sub 90 times sine phi sub 90. We already know what K is from our initial conditions, so now we will try to find expressions for v sub 90 and sine phi sub 90. And to proceed, we're going to zoom in on Q. But first, for simplicity, let's replace the velocity vector with a simple line segment tangent to the elliptical orbit at Q's position and remove the orbital path itself. Consider the angles alpha and omega shown here. Our goal now is to find the angle alpha in order to find the angle omega. Okay, let's zoom in. Here's the angle alpha in close-up, and let's consider two other angles. 1 and 2. As a direct consequence of the properties of ellipses, it turns out that angles 1 and 2 are equal. Let's label them both lambda. This property holds true regardless of the point at which one draws the tangent. Once again, I am showing you angle phi. Obviously, phi equals alpha plus lambda. This is equation 1a. Let's multiply both sides by 2. This is equation 1b. We can also see from the diagram that 2 times lambda plus alpha equals 180 degrees. This is equation 2. Let's subtract equation 2 from equation 1b. And we see that alpha equals 2 times phi minus 180 degrees. So if alpha equals 2 times phi minus 180 degrees, omega must equal 90 degrees minus alpha, or 90 degrees minus the quantity 2 phi minus 180 degrees, which is equal to 270 degrees minus 2 times phi. At the same time, we can see that the sine of omega must equal a times the quantity 1 minus e squared divided by a times the quantity 1 plus e squared. And the a's cancel out. Putting all of this together, we see that the sine of 270 degrees minus 2 phi equals 1 minus e squared over 1 plus e squared. Now we need to manipulate this equation a little bit using some trigonometric identities and a little bit of algebra. I'm going to move it onto some fresh workspace. So here it is, and as we work on this equation, I want to be able to indicate for you the trigonometric identity that we are using for each manipulation. Note that we are only going to be modifying the left-hand side of our equation. We will proceed slowly, step by step, without any further commentary until we get to the final result. Let's pause for a moment at this step and recognize how far we have come. We are very close to finding an expression for sine phi. All that is required is a little bit more algebraic manipulation, so let's go ahead and do just that. So here we are in a fresh workspace, and I will show you the algebraic manipulation step by step without further commentary until we get to the final result. We don't know the numerical value of sine phi, but we at least have a new expression for it. Let's see how that helps. Returning now to our general formula for k for our planet at an angular position of 90 degrees, let's update our progress. We can insert our newfound expression for sine phi and turn our attention to v sub 90. For our purposes, we don't need to know its direction or even the numerical value of its magnitude. We just want a new expression for its magnitude. This is where we can go back to our dv circle for planet Q to find out what we need to know. So here it is once again. And as before, we place the tail of V naught at an arbitrary point P2, as shown in the diagram. Recall that the distance from P1 to P2 is E times capital R. We can draw in a radius perpendicular to V naught, connecting with the dv circle at P3, as shown here. And we know that V sub 90 must have its tail at P2 and its head at P3. Triangle P1, P2, P3 is a right triangle, so we can use the Pythagorean theorem to find another expression for V sub 90. Thus, v sub 90 squared equals capital R squared plus e squared times capital R squared. Simplifying, we get v sub 90 equals capital R times the square root of 1 plus e squared. Now let's take this expression and see what happens when we plug it in for v sub 90 in our formula for k. We can divide the quantity square root of 1 plus e squared by itself, and we are left with 1/2 times r sub 90 times capital R equals k. So r sub 90 equals 2k divided by capital R, or in other words, L equals 2k divided by capital R. So just to review, we started with one general equation for an ellipse, and we found first one alternative expression for the numerator and then a second, namely L. Then we found an alternative expression for L involving quantities that we know. We know K, and we know R. When we do the math, we find that L equals 1.778 astronomical units. And so now we can plug that into our equation for our elliptical orbit. Specifically, we have found an expression for r sub I in terms of the two unknowns we are trying to find, E and theta sub I. Specifically, we can write it as 1.28 astronomical units equals the expression on the right. This is our second equation for these two unknowns. Here's the first one that we found earlier. And here's the second one that we just found. Solving for E and theta sub I algebraically would be quite a challenge, but thanks to the magic of graphing calculators, we can find the answers we're looking for rather easily. First, here is a plot of the first equation, showing E as a function of theta sub I. Next, I'm going to show you a plot of the second equation, once again showing E as a function of theta sub I. Note that negative values for E have no physical meaning in this context, and we need only be concerned with positive values for E. Finally, here is a graph of the two equations together showing the relevant points of intersection. From this graph, we see that E equals 0.778 and that there are two values for theta that satisfy the equation. This is due to the fact that the symmetry of the orbit around the major axis mandates that for any point along the orbit where the planet has a given speed and distance from the Sun, there must be a second point reflected across the major axis where the planet will have the same speed and distance from the Sun. As it happens, these values for theta in degrees would be 60 degrees and 300 degrees. We can sketch out these two solutions on our diagram of the orbit. If we put the planet at an angular position of 60 degrees and draw in v sub 60, we would find that phi sub 60 equals 2.023 radians, which was one of the initial conditions. The other solution would put the planet at an angular position of 300 degrees, and the following relationships would hold true. The magnitude of V60 equals the magnitude of V300, R60 equals R300, and phi 300 equals 180 degrees minus phi 60. And although the two are not equal, the sine of phi 300 equals the sine of phi 60. Now that we know the value for E, we can substitute it into our general equation for this elliptical orbit, as shown here. So, for example, if we want to go back and find the value for R at perihelion, when the angular position equals 0 degrees, we simply substitute in 0 degrees for theta, and we see immediately that R sub p must equal 1 astronomical unit. This concludes the final exam.